Welcome to The Explainer. Today, we are going to pull back the curtain on how machines learn to predict things. Seriously, this is the tech that powers everything from your streaming recommendations to incredibly complex medical diagnoses. We're going to break down exactly how it works, piece by piece. So, how does a machine predict the future? It really can feel like some kind of magic, right? But the secret isn't a crystal ball. Nope. It's all about finding hidden patterns and relationships in data that we already have. And then it uses those patterns to make a really educated guess about something new. All right, here's our game plan. We're going to start super simple with just one variable. Then we'll level up and add more features. After that, we'll get into the nitty-gritty of how machines actually learn, how we can tweak that process, and then, to wrap it all up, we'll walk through a complete example from start to finish. Okay, so to get started, we're going to keep things incredibly simple. Let's just imagine we want to predict the price of a house, but we've only got one single piece of information to go on, its size. So check this out. Here's our data. On the left, you've got the size of the house, and on the right, what it sold for. The machine's job, its whole goal right now, is to look at these points and figure out the best possible straight line that captures this relationship between size and price. And in the world of machine learning, that best fit line is described by this simple little function. Here, x is our input, right? The house size. The model's entire job is to find the perfect values for w. That's the weight, which controls how steep the line is, and b, which is the bias. You can think of the bias b as the starting price of a house before we even factor in the size. But you and I both know that a house's price isn't just about its size. I mean, the real world is way more complex, so our models need to be too. This is where we start adding more info into the mix. So to make our predictions way more accurate, we can start adding more features. Now, on top of size, our data also has the number of bedrooms, the number of floors, and even the age of the house. Every single new column gives the model more to work with, more context. So what happens is our simple little model has to evolve. Instead of just one input x, we now have a whole bunch of them. And that means instead of just one weight w, our model now needs a separate weight for every single feature. One for size, another for bedrooms, another for floors, and so on. The machine's job is to learn how much importance or weight to give each of these individual features. Okay, so this is the big question, right? How does the machine actually learn the best possible values for all those different weights in the bias? Well, it needs a goal. It needs a way to measure how good or, how bad its current predictions are. And this image just illustrates the concept perfectly. This 3D surface, it's called a cost function. I want you to think of every single point on this surface as a different version of our model with different values for w and b. The height of any point represents how much error that model has. The goal? Find the very, very bottom of the bowl, the one point with the absolute lowest error. And the algorithm it uses to find that lowest point is called gradient descent. The idea behind it is actually really clever. It just starts with a random guess, then it calculates which direction is downhill, which change will reduce the error the most, and then it takes a tiny step in that direction. It just does this over and over and over again until it finally settles at the bottom. Now, the size of those downhill steps that the algorithm takes is incredibly important. It's a setting that we actually have to control, and getting it just right is the key to training a really effective model. It can't be too fast, but it also can't be too slow. This speed, it's controlled by a setting we call the learning rate. You can think of it as the size of the steps the algorithm takes on its way down that error curve. And let me tell you, choosing the right learning rate is one of the most critical parts of training a model successfully. I mean, just look at the difference here. The blue line, that shows a good learning rate. The error drops nice and fast and then it levels off. But that yellow line, that's a learning rate that's way too small. Yeah, the model is learning, but it's taking forever to get to the right answer. But here's the real danger. If the learning rate, the step size, is too big, the algorithm just overshoots the target. It takes this huge step, lands on the other side of the valley where the error is even higher, and then it takes an even bigger step from there. The error just explodes, and the model completely fails to learn anything at all. We call this divergence. So after we've trained our model and we think we've found the best settings, there's one final absolutely crucial test. We have to see how well it performs on a separate set of data that it was not trained on. This is what tells us if the model has truly learned the underlying patterns or if it just kind of memorized the training examples. Okay, we've covered a lot of the theory. So now let's put it all together. We're going to run through a complete practical example to see what this whole process looks like from start to finish and how we turn all this math into meaningful, real-world insights. So the whole process really breaks down into 3 clear steps. First, we gather our data, that table of houses with their size, bedrooms, floors, and age. Second, we unleash our gradient descent algorithm to train the model, letting it figure out the best values for all our weights and the bias. And third, and this is the most important part, we interpret what the model has actually learned. And this is the real payoff. After all that training, our model gives us concrete numbers. The bias B tells us the base price of a house starts at $80,000. The first weight tells us that for every extra square foot, the price goes up by $100. Each extra bedroom adds $4,000. Each floor adds $10,000. And what's really interesting is the model learned that for every year a house gets older, the price actually decreases by $2,000. The math has become a clear story about what drives house prices. So the huge takeaway here is that this powerful technique isn't just for predicting house prices. Not at all. It's a foundational method that you can apply to predict customer behavior or medical outcomes or, well, nearly anything where a bunch of different factors contribute to a single result. The only question left is, what complex problem would you want to solve next?